Friends, welcome back to my YouTube channel. In this lecture, I am going to discuss some previous year questions of GATE which are based upon the concept of entropy and entropy generation. The first question that I am going to discuss is like this. The Clausius inequality holds good for options are for any process, then option B is for any cycle, and option C is only reversible process, and option D is only reversible cycle. And it was asked in the GATE Mechanical Engineering 2022, and it was in the set 1. So the Clausius inequality is cyclic integral of del q by t, which is less than or equal to 0, and this is equal to 0. In fact, cyclic integral of del q by t is equal to 0 for reversible cycle, and cyclic integral of del q by t is less than 0 for irreversible cycle. And cyclic integral of del q by t cannot be greater than 0. And if it is greater than 0, this is not possible. So you can say this is impossible for any cycle. And this inequality is valid for cycle, any cycle, both for reversible and irreversible. It is not applicable for any process. And so out of the given options, it's not valid for any process, and it is valid only for any cycle, and it is not valid only for reversible process. And so the correct, and it is not valid only for reversible cycle, it is also valid for irreversible cycle. So it is valid both for reversible and irreversible cycle, and when it is greater than 0 means the cycle is impossible. So option B is the correct answer. It is valid only for cycle, both for reversible and irreversible. It is not valid for any process, because the cyclic integral is evaluated for any cycle, not for any process. So next question is, for an ideal gas with constant properties undergoing a quasi-static process, which one of the following represents the change of entropy from state 1 to state 2? When you are going to calculate the change in entropy of an ideal gas, there are two equations which can be used, and those two equations are derived from those property relations, two property relations like this. One is TdS is equal to du plus PdV. TdS is equal to du plus PdV. This is a property relation. This relation can be valid for any process, be it reversible or irreversible, because you see in all these throughout this equation there are no path function terms, all are property terms. Temperature is a property, change in entropy is a property, change in internal energy is a property, pressure is a property, and dV is also for property. So it is not only valid for reversible process, it is also valid for irreversible process. So for any kind of process, be it constant pressure or constant volume, this is applicable for any process. Another equation is TdS is equal to dH minus VdP. These two are property relations, valid for any process. So from these we can derive the change in property for an ideal gas. If you want to derive that change in entropy from this equation 1, the equation will be like this. TdS is equal to du plus PdV, which implies ds is equal to du by t plus p by t dv. For an ideal gas, the relation is PV is equal to RT, where V is specific volume. So P by T is nothing but R upon V. So, and du for an ideal gas is nothing but CBDT. du is equal to CBDT. So this is CBDT divided by T, plus P in place of P by T, if I put R by V dV. So on integrating this ds, on integrating this, Cv is a constant for an ideal gas. So Cv dt upon T, and limit is from suppose T1 to T2. So plus R is a constant which can be taken outside, dV upon V. Suppose this is V1, this is V2. Now the relation is Cv ln T2 upon T1 plus R ln V2 upon V1. And this is one formula for calculating change in property of change in entropy of an ideal gas. Cv ln T2 by T1 plus R ln V2 by V1. And another formula that can also be derived from this equation, TdS is equal to dH minus VdP, that is like this, TdS. So this is integration of ds is nothing but delta S, change in entropy of an ideal gas, which is S2 minus S1. So this is the formula for delta S. And if you find out the formula from this relation, property relation, this will be like this. For an ideal gas, dH is equal to Cp dt and minus Vdp, from which ds is equal to Cp dt upon T minus V by T dP. And from ideal gas equation, Pv is equal to RT. So V by T is nothing but R by P. So this is Cp dt upon T minus R dP upon P. On integrating, delta S will be Cp ln T2 upon T1 minus R ln P2 upon P1. So these two formulas are used for finding out the change in entropy of ideal gas. One is Cv ln T2 by T1 plus R ln V2 by V1, and another formula is Cp ln T2 by T1 minus R ln P2 by V1. You see, this question was asked in GATE Mechanical Engineering 2018 and it was in the set 2. Out of the given options, we will see which option is correct. Obviously, this is the correct option because we have derived this. These two formulas can be used. One is Cv ln change in entropy of an ideal gas between two specified states, between two equilibrium states. Suppose the temperature of initial state is T1 and specific volume is V1, and final equilibrium states, T2 is the temperature and small v2 is the specific volume. Then specific change in specific entropy will be nothing but Cv ln T2 by T1 plus R ln V2 by V1. Similarly, change in entropy, specific entropy, can also be expressed as Cp ln T2 by T1 minus R ln P2 by P1. So this formula is not in the option. You see, you check the options. Cv ln T2 by T1, but no R term is there. And in fact, this is a term. This is an equation in which R is there and Cv is there. But here R ln, it should have been V2 by V1, not V1 by V2. Had it been V2 by V1, it would have been correct. So this is the only correct option. That is Cp ln T2 by T1 minus R ln P2 by P1. Next question is like this. 1 kg of air undergoes, for which R is 287 joule per kg Kelvin, undergoes an irreversible process between equilibrium state 1, whose properties are 20 degrees Celsius temperature and total volume is 0.9 meter cube, and equilibrium state 2, whose temperature is 20 degrees Celsius and volume is 0.6 meter cube. The change in entropy, that in fact this is specific entropy, joule per kg Kelvin, is we have to find out. And it was asked in year 2015 and it carries 2 marks. It was in the set 2. You know, it is in fact an irreversible process, but we know that delta S irreversible process is equal to change in entropy of reversible process between same two end states. Suppose state 1 is this one, this is an equilibrium state. State 2 is this is another equilibrium state. Suppose this is an irreversible process. But whenever we want to calculate change in entropy between two specified states, two equilibrium states, the integration has to be carried out along the reversible path, because you know between two given states this is a reversible process and this one is irreversible process. That is why it is represented by dotted line. So but we have to find out change in entropy between two given states, that is S2 minus S1, S2 minus S1, and this S2 minus S1 will be same for reversible process and irreversible process. Since we can't integrate irreversible process, we have to find out entropy along the reversible process between the same two end states. ये इक्विलिब्रियम एंड स्टेट सेम है लेकिन ये इरिवर्सिबल प्रोसेस है और इरिवर्सिबल प्रोसेस है. So we can calculate the change in entropy on reversible process, even though we are to calculate the change in entropy between two equilibrium states, and if the process is irreversible then we have to integrate along reversible process. So the formula is like this: for an ideal gas, change in entropy is nothing but mcp ln T2 upon T1, and this has been derived by integrating some properties just we derived in the previous question, this formula. And so integration is only possible along a reversible process. But since the entropy is a property of system, it is not dependent on path. So even though it has been asked to find out the change in entropy along an irreversible process between two specified states, we can do it by calculating change in entropy between the same two end states along a reversible process. So this formula has been derived from integration, and the formula is like this: mcp ln T2 by T1 minus mr ln P2 by P1. This is for change in total entropy, but we are to calculate the change in specific entropy because unit is in terms of joule per kg Kelvin and mass of air is 1 kg. So if you want to calculate change in specific entropy, that will be Cp ln T2 by T1 minus R ln P2 by P1, or I can use Cv ln T2 by T1 plus R ln V2 by V1. These two, out of these two formulas, anyone can be used, since only the equilibrium states are defined in terms of temperature and volume. So we will definitely use this formula. It will be convenient to use this formula. So the change in specific entropy will be Cv, value of Cv is 0.718 ln T2 by T1 plus 0.287 ln V2 by V1. But you see here temperature is same between two end states. Temperature at state 1 is 20 degrees Celsius and temperature at state 2 is 20 degrees Celsius. So this will be 0.718 ln 20 degrees Celsius in terms of Kelvin will 293 divided by 293. So this will come out to be 0 because ln 1 is 0. So now only this term is remaining. So this one will be the change in entropy, or delta S will be R ln V2 upon V1. R ln V2 upon V1. So this is R in terms of joule is 287. Of course in terms of kilojoule it is 0.287. So we have to put, since we have to find out the answer in terms of joule, so R we will take in terms of joule. 287 ln V2 is 0.6 meter cube. This one is specific total volume, of course. So 0.6 meter cube and this is 0.9 meter cube. In fact, this is specific volume because the amount of air is given to be 1 kg of air. So volume of 1 kg of air means this is specific volume. So 0.6 meter cube divided by 0.9 meter cube. So this is equal to 287 ln 0.667. This is equal to minus 116.225 joule per kg Kelvin. So in fact there is a decrease in entropy of air when it moves from this state 1 to state 2. When there is a decrease in volume, so there is a decrease in entropy. So next question is like this, question number 4. In fact, this question number 3 was asked in 2015 and it carries 2 marks. So a cyclic device operates between 3 thermal reservoirs as shown in the figure. Heat is transferred to or from the cyclic device. It is assumed that heat transfer between each thermal reservoir and the cyclic device takes place across negligible temperature difference. Interactions between the cyclic device and the respective thermal reservoirs that are shown in the figure are all in the form of heat transfer. So all these are heat transfers. So suppose this one is Q1, this one is Q2 and this one is Q3. These two heat interactions are towards the cyclic device and this heat interaction is away from the cyclic device. So we have to conclude the cyclic device can be a reversible heat engine, a reversible heat pump or a reversible refrigerator, a irreversible heat engine, an irreversible heat pump or an irreversible refrigerator. You see, in fact, we can find out whether it is a reversible cyclic device or irreversible cyclic device just by applying the Clausius inequality. And this was asked in the GATE 2008 and it carries 2 marks. For Clausius inequality, cyclic integral of del Q by T is less than or equal to 0, less than for irreversible cycle and equal to 0 for reversible cycle. So our first objective is to find out the cyclic integral of del Q by T. And if by convention we will take, while calculating the cyclic integral of del Q by T, we will take the sign positive when heat transfer is towards the cyclic device and we will take the sign negative when heat transfer is away from the cyclic device. So in this case, if you want to calculate the cyclic integral of del Q by T, cyclic integral of del Q by T, this is nothing but Q1 is again 100 kilojoule by 1000 Kelvin. Since 100 kilojoule comes towards the cyclic device from 1000 Kelvin. So this is 100 kilojoule divided by 1000 Kelvin plus another heat that comes from 500 kilojoule is 50 kilojoule 50 kilojoule divided by temperature from which this heat comes is 500 Kelvin and this is minus 60 divided by 300 kilojoule divided by Kelvin, because since this heat flows away from this cyclic device to a low temperature reservoir at 300 Kelvin, so minus sign is put before this. So on adding these 3 terms, this is 0.1 100 by 1000 and this is again 0.1 minus 0.2. So this is equal to 0 kilojoule per Kelvin. So cyclic integral of del Q by T is 0. That means it's a reversible device. It's a reversible cycle, in fact, reversible cycle. So these 2 options are not possible. These 2 options are eliminated. Now out of these 2 options, it can be a reversible heat engine or it can be a reversible heat pump or a reversible refrigerator. So which one is going to be correct answer? So that we have to examine. So these two options are not possible because the cyclic integral of del q by t is equal to 0 means it's a reversible cycle, be it engine or heat engine or refrigerator. That's a different thing. So you see, this is a reversible heat engine because here two heat interactions that are coming to the cyclic device are from high temperature, and this one is the low temperature to which heat is rejected. Low temperature to which heat is rejected. So total sigma q cycle, whatever heat that is coming to the cyclic device is 100 plus 50, 150, and heat rejected is 60 kilojoule. So what about the remaining energy that comes to this cyclic device? This is the heat that comes into this device, 100 plus 50, 150, and this heat is rejected to the low temperature sink. 150 minus 60, 90 kilojoule is the work produced by this cyclic device, 90 kilojoule. So out of some heat supplied to the cyclic device, some work is produced and some heat is rejected to a low temperature reservoir, and heat that are coming to the cyclic device are from a high temperature, and the low temperature, the reservoir to which heat is rejected is of low value. So that means, and some net work output is there, 90 kilojoule in this case. So obviously this one is a reversible heat engine. Had it been reversible refrigerator, heat would have been transferred from low temperature to high temperature and work would have been consumed. In this case, some work is produced, net work output is possible. So that's why it's a reversible heat engine. So option A is the correct answer.